Right, in this video I'm going to talk about special relativity, the first part of it anyway. I'm not going to be very comprehensive in this. It's not a thesis or anything, it's just what you need to know for the A-level course. Okay, so special relativity, what you need to know. There are two situations where the normal laws of physics don't apply. One of them is when things are very, very, very small, and the other is when things are traveling very, very fast. Now, the first situation is quantum physics, and you do a bit of that in the lower six, and then at the end of the upper six we do quite a bit of quantum physics. And then when things are traveling very fast, strange things happen, and that's called special relativity. The two consequences of special relativity that we need to know about are time dilation and mass increase. And in this video, I'm going to talk about time dilation. Imagine we have two cars, and the two cars have identical clocks that read exactly the same time. And what happens is that one of the cars, the car at the top, is going to go on a journey. It's going to accelerate. It's going to travel very, very fast. Maybe it's going to go to the moon and back, and it's going to come back. And then after its journey, we look at the clocks, and what we notice is that less time has passed for that car. Look at its clock and look at the car that didn't go anywhere, and you'll see that there is a difference. Now, the smaller amount of time, I'm calling that little t, and the larger amount of time, I'm calling that big T. Why is there a difference? Well, there is a difference because of something very interesting about light, and that is that light travels at the same speed relative to any observer. If you look at the situation on the left, if you were traveling on a skateboard at 3 meters per second and you chucked a ball at 2 meters per second, then to a stationary observer, the velocity of the ball would be 5 meters per second. However, imagine you were on a rocket traveling at 1 times 10 to the 8 meters per second, and on the front of the rocket there was a torch shining light. Now, to the person on the rocket, the velocity of the light would be 3 times 10 to the 8 meters per second. To a stationary observer, the velocity of the light would also be 3 times 10 to the 8 meters per second. And that's very strange. The speed of light is the same relative to any observer. And this has been proven experimentally many times. And it is as a consequence of this that time dilation occurs. And I'm not going to say any more about it than that. How much does time slow down? Well, we calculate that using something called the gamma factor, or the Lorentz factor. And looking here, gamma is big T over little t, and it equals 1 over the square root of 1 minus v squared over c squared, where v is the velocity of the fast-moving object, the one that accelerated, and c is the speed of light. A few things you should remember: the gamma factor is never less than 1. If an object is stationary, then its gamma factor is 1. As it travels faster, its gamma factor increases, but it only gets significantly bigger than 1 if you are approaching the speed of light. So in everyday life, this just doesn't apply. But for things like particles in a particle accelerator, then it becomes significant. So if you're traveling very, very fast, then gamma starts increasing significantly. Here's a couple of questions you can have a go at using those equations on the other page. Pause the video maybe, have a go at them now. And here are the answers. The first one, very straightforward, just putting the values of v and c in the equation. You get gamma's 1.47. For number 2, remember the gamma factor is greater than 1. It's big T over little t, the big time over the little time, so it's 2.4. To get the velocity, you'd have to rearrange the equation as I've shown here, and that gives you the velocity of 2.73 times 10 to the 8 meters per second.